Two independent teams just broke Claude Code and Codex with nothing but a fake product review and a forged GitHub comment. No exploit, no malware, just data. Here's the structural problem underneath all of this. When you type a prompt, that's one channel of input. But the agent also pulls in a second channel. Files it reads, web pages it browses, results from its own tools, comments on GitHub issues, and pull requests. All of that gets dumped into the same shared context window the model reasons over. The model then has to guess from formatting alone which parts are just information and which parts are commands it should act on. The agent data injection paper puts it bluntly: current agents do not isolate trusted data from untrusted data. That's not a bug in one tool, it's how the architecture works across Claude Code, Codex, and Gemini CLI. And here's the part that makes old defenses useless. This attack doesn't even need the model to mistake data for an instruction. It exploits something subtler: how the model reads structure where one field ends and another begins. Researchers at Seoul National University gave this a name: Agent Data Injection, or ADI. It's different from regular prompt injection. Regular injection tries to get an agent to read text as a command. ADI does something sneakier. It gets untrusted data misread as trusted data. The technique is called probabilistic delimiter injection. Attackers sprinkle punctuation-like characters into a field: an escaped quote, a curly quote, a bracket, a $sign. A normal program reads punctuation by strict rules. A language model reads it by guesswork, and that guesswork is exactly what breaks. Walk the whole chain start to finish. Step 1, the attacker plants a fake review on a shopping page. Step 2, the review hides an escaped quote and a line break inside the text. Step 3, right after that break, the attacker adds a fabricated extra button entry. Step 4, that fake entry reuses the real numeric ID of an actual button already on the page, because the agent's page reading tool numbers elements sequentially, so the ID is predictable. Step 5, the agent's read page tool returns this poison summary as ordinary page data, nothing flagged. Step 6, the model reads the fake entry as a legitimate part of the page's structure. Step 7, notice what didn't happen here: no persuasive language, no command, just a structural trick. Step 8, the user tells the agent to click read more. Step 9, the agent matches the attacker's spoofed button instead because it looks identical to a real one. Step 10, the agent clicks buy now and an unauthorized purchase goes through. This exact chain with screenshots is published in the researcher's own write-up. Across GPT-5.2, Claude Opus 4.5, and Gemini 3 Pro, ADI hit 31 to 43% success on structured data and up to 100% on web page data. Ordinary prompt injection against those same defenses scored 0.0 to 0.7%. That's the paper's whole point. Current defenses target instructions, not data, so ADI walks right past them. The same trick works against coding agents, just aimed at trust instead of clicks, and the paper shows two separate ways in. Chain 1, an attacker posts a comment on a GitHub issue or pull request, and the delimiter trick forges its own author line so it reads like a real maintainer wrote it. The coding agent, Claude Code, Codex, or Gemini CLI working that issue ingests the comment as ordinary data pulled from the GitHub API, not as a user instruction. Because it already trusts that maintainer, it treats apply the fix as safe and either presence or in auto mode runs the attacker's actual command. If a developer approves what looks like a routine fix, that command executes on their machine. Chain 2 is quieter. An attacker submits a pull request whose description fabricates a fake record, text that reads exactly like a completed clean test run the agent never actually executed. The reviewing agent treats that fake history as trusted metadata about work already done, judges the code safe based on a check that never ran, and merges the PR. No RCE on anyone's machine, just malicious code pulled straight into the project. One clarification: Claude in Chrome, the browser agent, is a different product from Claude Code, the coding CLI. Both got hit, but by separate chains. Vendors got word early too. Anthropic, OpenAI, and Google were all notified back in January 2026, months before any of this went public. The independent Friendly Fire team from the AI Now Institute built a separate proof of concept 3 days later. No hooks, no plugins, no MCP servers, no config changes, just a doctored copy of a real open source package, geopy. Inside, a precompiled binary called code policies carrying a hidden payload, a decoy go source file to make it look like legitimately compiled tooling, a wrapper script called security.sh, and a short injected section added to the bottom of the README. Quick note, I post one of these daily, subscribe if this is useful. They tested it against Claude Code, versions 2.1.116 through 2.1.199, running Sonnet 4.6, Sonnet 5, and Opus 4.8, and separately against Codex CLI 0.142.4 running GPT-5.5. Both fell for it in their default auto-review mode. Ask Claude Code or Codex to security review this library, and it reads the README as trustworthy documentation, decides the binary is a legitimate analysis tool, and runs it. AI Now Institute puts it bluntly, there's no patch to wait for. The versions they tested aren't a vulnerable range to fix, they're just what happened to be installed when the exploit ran. This isn't a company that ignores security. Separate research found Anthropic shipped more than 30 security-relevant patches to Claude Code between April and June 2026, most of them silent version bumps with no public advisory. Fast at fixing things, just not big on announcing them. There's no confirmed fix for this exact class yet though. ADI and Friendly Fire were both disclosed after that window. There's proof this is fixable. ChatGPT Atlas resisted the click hijack attack completely because it uses randomized, unguessable element IDs instead of predictable sequential ones. Claude in Chrome, Anti-Gravity, and Nano Browser, the other browser agents tested, all use sequential IDs, and all three fell for the fake button trick. One engineering choice, one different outcome. Full data provenance, always knowing exactly which upstream source contributed which piece of context, blocked every attack the researchers tried. It also broke normal agent functionality, which is exactly why no vendor ships it by default. Now here's the part most videos on this topic skip. Your agent reads more than the data you hand it. It also reads its own configuration, and that config is leaking. Here's what an exposed MCP config looks like. A typical MCP server's block in Claude Code or Cursor, with an API key typed straight into the JSON as plaintext. That file gets committed to source control the same way a vscode settings file does and shared across a whole team. The fix is one line. Swap the raw key for an environment variable reference, so the actual credential lives in a gitignore.env file or a secrets manager, never in the config itself. GitGuardian scanned public GitHub and found 24K unique secrets exposed inside MCP configuration files, and 2,117 of those were still live, active credentials, not just plausible-looking strings. Break it down by type, and it maps straight to the tools developers wire into MCP. Google API keys at 19.2%, Postgres connection strings at 14%, Firecrawl keys at 11.9%, Perplexity keys at 11.2%, Brave search keys at 11%. A separate scan of MCP server hosting repos on GitHub, over 3,800 of them, found 202 leaking at least one secret. That's 5.2% of the sample, mostly bearer tokens and API key headers. GitGuardian's own diagnosis is blunt. Popular MCP setup guides tell you to put API keys directly into config files, command line arguments, or connection strings. Bad advice in an official quick start spreads at ecosystem speed. None of this is unfixable, and Anthropic's own docs list real mitigations. Turning on sandbox mode isolates file system and network access for bash commands, and Anthropic says it cuts permission prompts by 84% in internal use, without ever putting Git credentials inside the sandbox. Claude Code's WebFetch tool already runs fetch pages in a separate context window, specifically so a malicious page can't inject straight into your main session. New MCP servers require trust verification before first use, and Anthropic doesn't audit third-party MCP servers itself, so the real guidance is, write your own or only use ones from providers you actually trust. For anything that touches an untrusted repository, like a security review of a library you didn't write, run it inside a dev container or a VM, so even if the injection lands, the blast radius stays contained. Even short of that, adding random tags to field names cut ADI's success rate from about 49% down to about 29%. And Anthropic says this outright. No system is completely immune to all attacks. Review suggested commands before you approve them. Don't pipe untrusted content straight into the agent. Verify changes to critical files by hand instead of trusting an automated pass end to end. Bring it all together and the checklist is short. Poison data, sandbox mode and isolated web fetch contexts, forged identity, review every suggested command before you approve it. Untrusted repo reviews, run them in a container or a VM. Leaky MCP config environment variables, never hard-coded keys. This isn't going away with a patch. It's an architecture problem, and the fix that actually works breaks the thing that makes agents useful in the first place. Until vendors accept that trade-off, sandbox everything, review before you approve, and never let a maintainer's comment be the last check. See you in the next one.